That's the equation. But only if that's your rate equation, right? Just because it's A plus B goes to C doesn't mean that your rate equation is K times the concentration of A times the concentration of B. Okay? So again, sometimes you'll be asked to derive the rate equation. Sometimes it'll be given to you. But you can certainly imagine a problem where we started all the way back with, here's a reaction mechanism, derive a rate equation, and go through all of the steps that we've just done, and finally you end up at a solution. I'm not saying we're going to have that, because it puts a lot of pressure on you. You make a mistake early and the whole problem falls apart.
Is that an elementary reaction?
No, because remember that it's A plus 1/2 B goes to C. Yeah, so this is not an elementary reaction rate equation. But this isn't an elementary reaction either, right? All right, so now we can substitute in some numbers. Well, first we'll simplify a little bit as we substitute in CaO squared. All right, everybody see where I got that? And so if I tell you now a rate constant, and an initial concentration, which I'm going to change from the rest of the problem because they're changed in the notes. Then what do we want for Levenspiel? What is Levenspiel a plot of? -1 over RA as a function of x. So that's what I'm going to solve for. It's 1 minus 0.14 x squared, that denominator, divided by 2 times 1 minus x times 0.54 minus half of x. Okay, and now what can I do with that, right? I can make that plot, or I can just use the numbers directly and I can solve for the volume of a reactor. So just to remind you what those formulas are, right? So that's what you've been using in your homework. This is the integral form, right? So this would be for a PFR. It's a little bit simpler for a CSTR. So now we have the equation 1 over RA written in terms of conversion and nothing else, right? We can't leave volumes over here because volumes are also a function of conversion. We can't leave concentrations over here because concentrations are also a function of conversion. The only way that we can actually carry out this integral is if we put all of those conversion dependencies into the final form. So that's what this chapter is about, is how to do that, depending on whether you have a batch or flow system, isothermal, constant pressure, all those different things that can be changed. Okay, so we plug that into here, and then you can solve. Again, that's just for an isothermal reactor, which the next couple of homeworks will be about isothermal, and then we're going to have a test, and then after that test, things are going to get much more hard, much more difficult. Okay, this course, the first part of this course, the first part of the test, the first test is much easier than the second. Just to let you know.
The first test of freebie?
What do you mean?
A freebie?
I don't know what a freebie means. Huh?
Like really easy?
I'm hoping it'll be easier, but I haven't taken it before. It's been some years since I took a test on this stuff. But it'll be easier than the second. I can almost promise you that. Because in the second one, we're going to deal with non-isothermal reactions. So suddenly you got to deal with simultaneously heat and material balances as you have a reactor. So definitely things get harder. We'll also deal with a little bit of mass transport as well, which is never easy. But this first test, to me, is just algebra. So hopefully, you guys will find it simple as well. Okay, so that leads into the next chapter. So again, this is how the book has organized things. Mole balances is where we started. That led to design equations. We actually started here, but that's okay. You guys know how to get rate laws, right? And then we have this chapter we just talked about, stoichiometry, which is all about concentrations as a function of conversion. And now finally, we can integrate to calculate the volume. For a given conversion. Of course, I could also give you a volume and ask for a conversion. All right? So any questions about this? This is what we've done throughout the class so far. This all fits? Okay. So let's look at a batch reactor. And so we want to take ethylene oxide, react it with water. We have some sulfuric acid present, and we make ethylene glycol. Which is that. Okay? That's the chemistry, and then I'm going to make the chemistry a little bit simpler. Right? Don't forget too much of the chemistry, please. But yeah. What we can use, since we're not, I don't think in this example we're going to be talking about the rate laws, you can just remember things as A plus B goes to C. Okay, so we have our batch reactor. Inside we have A, B, and C. The initial concentration of A is 1 kilomole per meters cubed. Initial concentration of B, large. What do we mean by that? What's the medium of this reaction? Water, right? So this is just in excess the whole time. The initial concentration of C is 0. And we want to measure concentration as function of time. All right, so we start where? What was the first box I just erased? The change in A with respect to time is equal to the rate of A times the volume. Okay? And I can rewrite that in terms of conversion. The change in conversion with respect to time is equal to the rate of A times volume, now divided by the initial moles of A. Okay, again, I could maybe try to derive a rate law if I were given what the mechanism was. But sometimes you're just going to be given the rate law. So negative RA is equal to rate constant times the concentration of A. Right? So just a simple first order rate law. Notice that the concentration of B is not there. Any guesses why? It doesn't really change, so it's just going to be folded into this K, right? So if I had it, it's essentially the same as CB not the whole time, and so it's just going to end up inside here. You wouldn't actually observe it because, again, it's not changing. It's in excess the entire time. All right, now I can write out that stoichiometric table. The table's a little bit different than the one that I put on the board to start the class because that was a flow reactor. But we put this one on the board last class, and we'll put it up again. Species A, B, C. Do we have any inerts? No, not that you've been told about, which generally means you can neglect them. Yeah, if you're doing this in a room, there's probably dissolved oxygen in the water or something like that, but if you haven't been told about them, they're probably not going to show up.
Can you say the catalyst?
Say that again?
Can you say the catalyst is in there?
You wouldn't. It's not an inert species. It's a conserved species. But I wouldn't describe it as inert because that implies that it doesn't react. But you're right that the amount of it doesn't change or shouldn't change if you don't have deactivation or some other process. In an ideal world, it doesn't change. Okay, so the initial concentration here is NaO. This is this theta B times NaO. Initial concentration of C was 0, right? We didn't have anything in there to start. And then we look at the change. And this is minus NaO times X. This is also minus NaO times X. Because the stoichiometry of this was just A plus B goes to C, right? The stoichiometry is pretty simple. And then over here, it's just positive NaO X. And so remaining so I can add these up, and I get the total equal to the initial moles minus NaO times X. I can add these up too. Does the volume change for this reaction? Why not? Huh? You wouldn't see it here, so don't look for it. It's a batch reactor, that's part of it. So for a batch reactor, what matters? What if I have a batch piston, a gas phase reaction in a piston? Does the volume change? Yeah. What if I have it in a rigid vessel? Does the volume change? No. What about a liquid phase reaction? Generally, always no. Okay, within Fogler, I don't know that there are any homework problems. You're not going to have a test problem where the volume's changing in a liquid phase reactor. Does that mean in real life volumes don't change in liquid phase reactions? Right, of course they do. Usually a small amount, especially if you have a dilute reaction. Okay, because most of the A goes to C in this case. Most of the consumption of the ethylene oxide in order to form ethylene glycol, it's not that big of a deal. Yeah, ethylene oxide and ethylene glycol might have different molar volumes. That might mean that the volume might change a very, very small amount. But if they're both dilute species, what's the volume, what's the density of my solution? Same as water, right? It's constant, it's just whatever water is. Okay, so we can start by saying the volume is equal to the initial volume. That's always nice. Concentration of A is then Na over V. And since this is constant, I don't have to worry about it changing. I can just put the initial concentration times 1 minus X, which is this from this formula. All I've done is take this formula, divide by V, and so Ca Na naught over V just becomes Ca naught. So step 4 in this, you see step 1 through 3 here. Why do I need to stop at the concentration of A? I could write out the others, but do I need to for this case? Right, because the rate law only depends upon A. So don't forget why you're doing this. The reason why we're writing the concentrations in terms of conversions is so that we can substitute them back into the rate law. Okay? So that's what this says, is combine what you have from steps 1 through 3. So, starting with step 1, dx dt is equal to minus RAV over Na naught. Do we have the rate law? Yeah, so what do we substitute in, right? Let's put the rate equation in there. So now we get because this minus, that's also minus, so K, Ca, V over Na naught. Okay?
Can't the rate law ever have products?
Yes. Rate laws can have products, absolutely. Again, you would have to be given a mechanism that would lead to that,
Oh, true.
or I would just have to tell you, here's the rate law, and guess what? There's a product term in it. Okay, this simplifies to just, hold on. So we substitute this in next, Ca naught times 1 minus X. A lot of this stuff drops out. You just get a rate constant times 1 minus the conversion. We probably have room. So what was step 5 on our little series of boxes? Right. So, integral from 0 to x of dx over 1 minus x, which is just taking this and rearranging it. Okay? And so if we do that integral, we get that final form. So the log 1 minus c conversion is equal to kt. So taking that, you can also write it like this. There's a couple other forms.